To some people, solar power might seem kind of strange or even futuristic, but it's actually really quite common. You might have a solar-powered watch on your wrist or solar-powered lights in your garden. And if you live in 2001, you might still have a solar-powered pocket calculator. Most spaceships and satellites utilize some form of solar power, and NASA has even developed a solar-powered aircraft. As climate change becomes more and more of an issue, I think there's little doubt that solar power will become an even more important form of renewable energy. So if we are, in fact, going to be relying more heavily on this technology, then it probably wouldn't hurt to at least understand the basics of how it works. Solar power is the term we use to describe the conversion of sunlight into electricity, so it's probably worthwhile to discuss just how much energy we can get from the sun. According to the World Meteorological Organization, on average, every square meter of the Earth receives a consistent 120 watts of solar energy. In other words, you could stand a 100-watt table lamp on every square meter of the surface of the Earth and light up the entire planet using just the sun's energy. And that's the good thing about solar power. It's practically unlimited. But in order to tap into this unlimited resource, we first have to clear a pretty big hurdle. The energy from the sun arrives at Earth as a mixture of light and heat. The light is what makes plants grow, providing us with food, while the heat keeps us warm enough to survive. The problem is we can't use this light or heat directly to power a TV or charge my cell phone. We have to find some way of converting this solar radiation into some form of energy that we can more easily use, like electricity. And that's exactly what solar cells were made to do. The key component in most solar cells is silicon, which is a semiconductor. And in case you forgot, a semiconductor is a material that can conduct the flow of electricity, but is just really bad at it. A solar cell is basically a silicone sandwich where both layers have been specially treated or doped so that they will allow the flow of electricity, but only in a very specific way. One layer is doped so that it has more electrons than usual, and we call this the N-type silicone. The N just stands for negative because the addition of electrons gives it a net negative charge. The other layer is doped in the opposite way so that it has fewer electrons than it would under normal circumstances. We call this the P-type silicone, P standing for positive because it does in fact have a positive charge. So when we place the N-type silicone on top of the P-type silicone, the atoms at the junction between the two layers begin exchanging electrons due to the imbalance of their electrical charges. This causes an electric field to form at the junction of the two layers, which prevents any electrons from crossing from one side to the other. And this electric field becomes the middle layer of our silicone sandwich. So now we have this: a top layer with a negative charge, a bottom layer with a positive charge, and an electric field separating the two. Now we connect a wire to each layer with a lamp in the middle, and we're ready to start collecting light from the sun. Photons are particles of light, and when a photon hits one of the silicone atoms inside the electric field in that middle layer, it knocks loose an electron, which then slingshots out the negative side through the wire, powering the lamp and then back into the positive layer. And this happens all the time as the sun is just raining down photons onto solar cells, knocking loose loads of electrons that power that lamp and that TV and that iPad, and that is how solar cells convert sunlight into electricity. I think. Actually, I'm not sure about any of that.